Hi, my name is Skylar Moe, and today I will be presenting Lab 4 of Physics 2211, Oscillations and Energy. So today our purpose in this lab is to model the motion of a mass on an oscillating spring. We will introduce comparative analysis between the graphs of motion and energy, mainly predicted motion versus actual motion and energy changes, delta E, delta KE, delta UG, and delta US. As always, Newton's fundamental laws apply, and we will continue to use Newton's second law, F equals ma. Our key equations we use are the period, the force of a spring, the force of gravity, the energy of a spring, the energy of gravity, and kinetic energy. The intuitive equations are F net equals ma, the position update formula, and the velocity update formula. So for our initial conditions and calculations, we have the spring has a mass of 0.402 kilograms and length of 0.7 meters. First, we calculate our period by looking at the T versus V and finding the average of 3 periods. Here we have our tracker video, so we examine the motion and track the motion of an object moving in an oscillatory motion with the spring and a pendulum-like period. So for our next slide, we calculate our stretched length by subtracting the extended length and the relaxed length. So we use F equals ma to determine this, and our relaxed length is 0.127 meters. And then to find our spring constant, we work backwards by using the equation for period, T equals 2 pi square root m over k. Here we outputted our data with our .csv and Excel data, and this is the graph I formulated. Here we have the glow script code. These are the fundamental equations to find energy, as well as to find L. Here we have L is equal to ball position minus spring position, L hat, and then S. Here we have our initial energy is equal to our final energy to satisfy our energy equation. Then we have the force of gravity, the force of the spring, and the net force. Then we have our velocity update and position update formula. Then here at the bottom we have our kinetic energy, change in kinetic energy, gravitational energy, change in gravitational energy, spring energy, change in spring energy, total energy, and change in total energy. So this is what happens when you run the code. In order to do this, we had to take our CSV file, the tracker video, and put the data in a glow script. Here our blue ball is the observed data, and the red ball is the computational data. And at the bottom is our position and energy graphs. Here are our energy and positioning graphs. We have some discrepancies between the computational model and the observed model. The computational model does not account for things such as friction. And then we have our energy graph, the orange line representing the total change in energy, the green line being the spring energy, the red line being the kinetic energy, and the blue line representing the gravitational energy. So to answer some questions to wrap it up, for our model system, is the energy principle satisfied? Yes, since change in E stays at 0, this would satisfy our energy principle. This means that no energy is exiting the system and is telling that our fundamental laws of energy are completely satisfied in our lab. And then I did 2 separate estimates of oscillation, and for X I got 1.614 seconds, and for Y I got 1.519 seconds. The periods are different because they rely on different components. Y period is most affected by spring stiffness and mass, while X moves as a pendulum and relies on gravity and length.